Hello everyone, my name is Denis Antipov, and in this talk I will tell you about the online algorithm selection and when it can be helpful to switch from one algorithm to another. To explain you the idea of online algorithm selection, imagine that you have a race where first stage has an asphalt surface, the second stage goes through a desert, and the third stage goes through the ocean. And there are cars for each of those surfaces which can be good, like it's a sport car, then some kind of a buggy, and then a boat. But there is no car which would be quite good at all the stages, and the perfect solution to go through this race is to use one car, a sports car in the first stage, then switch to the buggy until you reach the ocean, and in the ocean switch to the boat. It will give you quite a good time when you want finishing this race. And this idea can be translated to selecting algorithms for optimization, which also in some sense go through the race as they search for the optimum. And imagine the situation when we have two algorithms and we know how they perform through time. So let's say on x-axis we have time, on y-axis we have the best function value that those algorithms found, and let's say that the first algorithm, it performs quite well at the beginning of optimization, but then it slows down, while algorithm 2 has roughly the same speed all the time. It means that if we start with algorithm 1 first, and as soon as it becomes slower than algorithm 2, we switch to algorithm 2, then we get a hybrid algorithm which becomes faster than both algorithm 1 and algorithm 2. So this is a simple idea of how to switch between algorithms, but when it comes to implementation of this idea, there are many questions which arise. For example, how do we pass information of what the first algorithm found to the second algorithm to initialize it with? How should we choose the algorithms for our portfolio between which we can switch? How we can detect an optimal switching time, and actually what should we expect from this technique compared? Like, does it even make sense? Does it give some reasonable speed up? And to answer all these questions, we perform runtime analysis, as you could have guessed, since we are at theory session. And this runtime analysis considers switching between different evolutionary algorithms. So, why evolutionary algorithms? A typical scheme of an evolutionary algorithms can be seen in this slide. So they start with initializing some population of solutions, which are usually chosen randomly from the search space, and then they perform iterations. First they select parents, then they change them through mutation and crossover, and then they select which individuals should survive into the next generation until some termination criterion is satisfied, and if it's satisfied, then they return the best found solution. And it's easy just to insert algorithm selection in the end of each iteration. So let's say that we run an iteration of one algorithm, and if we decide to continue, we can see, should we change to another, switch to another algorithm which actually involves how we select parents, how we vary them, and how we select individuals for the next generation. So how to choose a setting to study the algorithm? The idea is that the performance of the algorithms in our portfolio between which we switch should be very different at different stages of optimization. And the inspiration for such a portfolio can be drawn from the recent work of me with Maxime and Benjamin, which was published at TILO 2025, in 2025, where we showed that the 1 plus lambda comma lambda j actually has quite a good performance in the late stages of optimization of 1 max. Namely, if it starts in distance d from the optimum, it finds the optimum itself in square root of n d log d fitness evaluations. And it's well known that most of the mutation-based evolutionary algorithms, they can find this optimum starting from the same distance in n log d iterations. which is much more than this one. But it's also well known that simple mutation-based algorithms like the 1 plus 1a, they are faster than the complicated 1 plus lambda comma lambda j in the early stages when getting progress is quite easy. So this leads us to an idea that we should consider a setting where we optimize 1 max. We start with the 1 plus 1a and switch to the 1 plus lambda comma lambda j closer to the optimum. So given all the information that we have, it seems a perfect setting to study how to switch between algorithms. So let us do it more precise. So the function that we study is the 1max. It's a pseudo-Boolean function defined on the set of bit strings, and it returns the number of 1 bits in its argument. And most evolutionary algorithms, they start with here in the middle of the slope, where the bit strings have roughly half zeros and half ones. And then as they increase the number of ones in the bit string, they usually struggle to find the last 0 bits to flip. The algorithms that we consider are like more general than 1 plus 1a. It's 1 plus lambda a. So this algorithm is mutation-based A, where we keep only one individual x as a population, and in each iteration we create lambda offspring, each by flipping each bit with probability 1 over n. So and the best of this lambda offspring is created as the mutation winner y, and if the mutation winner y is not worse than current parent x, then it replaces its parent, and next iteration starts. The 1 plus lambda comma lambda j is a theory-driven algorithm which is more complicated than this, and it also stores only one individual, but its iterations consist of several phases. First, in the mutation phase, it chooses some number L from the binomial distribution with parameters n and lambda over n. So it flips lambda bits on average. Yes, because L is the number of bits which we flip in each offspring in this stage. So we create lambda offspring independently, and in each offspring we flip L bits. The best offspring is chosen as this mutation winner x prime, and then we perform crossover and create another lambda individuals, each by taking each bit from x prime with probability 1 over lambda, otherwise from x. So the best offspring is chosen as crossover winner y, and if this crossover winner y is not worse than its parent x, then it replaces its parent. So now, which tools do we use in our analysis? Well, actually we use tools that have been developed before. It's fixed target and fixed target analysis. Fixed target analysis aims at estimating the time that the algorithm needs to reach some particular fitness value. So how much does it take the algorithm to get a good solution? And fixed stat analysis aims at estimating the time that it takes the algorithm to find the optimal solution when it starts with some nice or some solution that is already better than just a random one. So in this paper we delivered the first results, fixed target results for the 1 plus 1a on 1 max. So we showed that to reach distance d with the 1 plus lambda a, we need n lambda log lambda divided by log lambda, like this number of fitness evaluations, and I just know that it's a very rough estimate, and most probably it can be improved, especially for the distances that are closer to n over 2, but this simple bound was enough for the result which we got in this paper. And for fixed stat results, they already exist for the 1 plus lambda comma lambda j in the paper which has already been mentioned by me. So, and when we consider a simplified case, when we don't use the 1 plus lambda but just 1 plus 1a, and we switch to the 1 plus lambda comma lambda j, we decided first to see what happens when we know exactly the distance at which we need to flip. And imagine that our algorithm first runs 1 plus 1a, and as soon as it reaches distance d from the optimum, it switches to the 1 plus lambda comma lambda j. It's not a realistic setting, but let's say that we know d. and for the moment. And we showed that if d is chosen, roughly speaking, n over polylog of n, and if lambda is chosen roughly logarithmic in n, then the expected runtime of this algorithm that switches from 1 plus 1a to the 1 plus comma lambda j is n log n, which is much better than the runtime of the 1 plus 1a, which is roughly n log n, and it's also better than the best possible performance of the 1 plus lambda comma lambda j with fixed parameters, it's important, which is n square root of log n up, like where I avoided sub polylogarithmic factors to make it easier to read. And also interesting that this result holds even if we replace the 1 plus 1a with 1 plus lambda a with not too large population size, where the population size is at most, let's say, double logarithm of n. But okay, let's come to more realistic situation when we don't know what is our distance to the optimum. In this case, it makes sense to switch from the simple 1 plus 1a to a more complicated 1 plus comma lambda j, when on average we already spent at least lambda evaluations and have no progress, because it means that the more complicated mechanism of the 1 plus lambda comma lambda j doesn't spoil our fitness evaluations. Does it mean that we need to switch after lambda consecutive fails to get a progress? Actually not, because if we switch too early, then we can get quite a bad performance, because the 1 plus lambda comma lambda j can be quite bad in this interval of 1 max values. So we can switch a little bit more conservatively. Let's say that after lambda log n unsuccessful iterations of the 1 plus 1a, when we don't get any progress, we can actually just say that, okay, now we are quite sure that the 1 plus 1a is not effective anymore, we can switch to the 1 plus lambda comma lambda j. And we showed that using this simple switching algorithm, the runtime is the same as when we know the d, which is n log n. Of course, it's considered, it's conditional on that we choose the right population time for the 1 plus lambda comma lambda j, which is approximately logarithmic. So, important notice is that online algorithm selection is very close to the hyperheuristics. And hyperheuristics, they usually aim to choose lower level heuristics, and they can really be described with a very similar scheme as online algorithm selection. But we see it as a slightly different paradigm, because online algorithm selection aims at learning algorithms' behavior and run algorithm until our algorithm selection algorithm understands that it's not efficient anymore. While hyperheuristics, they usually use some predefined mechanisms, like, for example, using random heuristic or reuse some successful heuristic, and they often change only one component. But nowadays, like when hyperheuristic become more and more complicated, they become more and more closer to online algorithm selection, because they also learn the effectiveness of each lower level heuristic. But I would say that this is actually a good topic to discuss in our community, not to get to different directions of research, and let's leave it for discussions. But at this moment, I would just to say that we also used a more hyperheuristic approach for selecting between the 1 plus 1a and 1 plus lambda comma lambda j, and this approach can be described as following. Like, let's say that if in the previous lambda iterations there was no progress, then we run an iteration of the 1 plus lambda comma lambda j, otherwise we run an iteration of the 1 plus 1a. So it's a simple hyperheuristic with like a little bit of memory about what progress we had before. So note that it switches to the 1 plus lambda comma lambda j after lambda unsuccessful iterations, which is less conservative than for our online algorithm selection, but this is because we can switch back to the 1 plus 1e. And interestingly, we also proved that this hyperheuristic can also solve 1 max is in the same asymptotic time, which is n log n. So, to conclude my talk, online algorithm selection can outperform the algorithms from its portfolio, as we showed in this walk, and the first proof when we get an asymptotical speed up, except for some artificial examples for hyperheuristics where the function required to be able to switch both 2 or 3 bits. And the follow-up questions are: how robust is this switching mechanism? And, well, we have already answered this question in our PPSN paper. The answer is yes, it's quite robust to more complicated function landscapes. And also another question is: how big should the portfolio be? Because we see that even 2 algorithms can give us a speed up, and obviously if we have different 1 plus lambda comma lambda j's in our portfolio with different lambda sizes, then we can just emulate the adaptive 1 plus lambda comma lambda j, which solves 1 max in linear time. So what is the minimum size of the portfolio that achieves this? Because the smaller the size of the portfolio, the easier it is to choose between the algorithms. So that's it. Thank you for attending this talk, and I hope to see you at GECCO.